Okay, so last time we were, let me open this. So last time we were talking about how to develop a hazard map. We have the two lectures, right? So this is the third lecture, so we need to end this. So our target is to develop a hazard map like this. So to do this, we understand that there is a hydrologic modeling that we need to go through, and there is kind of process of hydrodynamic modeling that we need to go through. This hydrodynamic modeling using the output from a hydrologic model, which is a hydrograph, and using it as a boundary conditions. And we saw how we can develop a geometry for our study area. And this geometry, we add some boundary conditions. This boundary conditions is a hydrograph, like what is the water flow at this boundary conditions? And we stop at the definition of the boundary conditions and inserting the hydrograph. So if you guys remember from last time, we had our geometry, the mesh that we talked about, and I showed you how if we would like to add a break line, the break line allows you to develop a mesh around some locations. Okay, so let me do something here. Okay, here, imagery. So this is our mesh, and we defined two boundary conditions for our study area. We have one in the upstream at Lumber River, and we had another one. But I told you last time that you can add as much boundary conditions as you want. Like I did too. You can have a one here. You can have a one here at this stream and a one here at this stream. Okay, you can add as much boundary condition as you want, but this will add more complexity to your model, and you will have to pay for that. It will take lots of time to run. So this is one of the it will be more accurate, definitely. But maybe if you, let's assume that with two boundary condition, you got flood depths maybe here, let's say 2 feet. But if you added all these complexities and you are getting 2.05, so does it require all this kind of modeling? So it's the same thing like you are designing a building and you are not using ETABS and you're using ANSYS with a solid element, not shell element and not frame element. So it's the same thing. Does it worth it that you use solid element on ANSYS to solve a building, or ETABS is very good? So this is the same thing. All right, so once you are done with your geometry and you saved your geometry, and that's what we stopped at last time, we're about to define how the unsteady flow will look like. So we went to edit, and then we went to unsteady flow. And when we open unsteady flow, this is not the. Yeah, so here, edit. Let me go back to geometry. So you guys found in the geometry, I have two boundary conditions. I just want to show you an example if you want to include more boundary conditions. I showed this example for you. We had a boundary condition here, another one here, another one there. So we have multiple boundary conditions. So you can do either. And if you see, let's close this slide. I have bunch of break lines, like a break line here to catch some elevations and a break line here, and one on the road, like I have a road here. So as you can see, I put all the way on the road because the road on a higher elevation. So I have a break line. I have a break line at the levee. So lots of break lines to capture all the feature in my floodplain. So I talked to you about the boundary conditions as a water flow. We have another boundary condition that we need to define where is the downstream is. Where's the downstream? Where's the water? I know that the water is flowing from here, but at the end of your geometry, you will have to define that there is a downstream, ES, here. So this is one thing that you need to add to your geometry. And you need to define how is the water is flowing from the upstream to the downstream. So we will say that it's flowing by gravity and there is a friction, and we need to assume what is the friction coefficient. And we usually use 0.01 friction coefficient of the land. However, friction coefficient can be different based on the topography, based on if it's moving in a solid surfaces, if it's moving in a forest. So this is how the friction coefficient can change. So let's see in our model how we draw a boundary condition for the downstream. So this is our example with two boundary condition in the upstream. Let's okay, here. So not this one. Let's close this one. Yeah, this one. This is my two upstream boundary condition that they will have a boundary condition flow hydrograph, which is a water flow over time. And I draw another one in the downstream. It will not have a boundary condition hydrograph. It will have a boundary condition normal depths. We will say that the water is moving toward this downstream with a normal depth, with a normal depth reference of the land that the water is moving in. And once I'm done, and you will have to make sure that your mesh is well aligned with this boundary condition. If you are not sure, you click edit 2D flow area, and then you say force mesh recomputation. Because sometimes you draw a break line, but you forgot to align the mesh around this break line, or draw a boundary condition and you forgot to, because sometimes you have multiple break lines, like the project that I showed to you, or you have multiple boundary conditions. So you need to make sure that this mesh is aligned with everything that you draw. So you click force mesh recomputation so it can read all the inputs that you have. So let's double check. Let's make this force mesh recomputation. Okay, we'll need to wait. It will take maybe 1 minute, depends on the number of mesh we have, less than 1 million. So it will take maybe a minute. So, and the next step is to plug in the flow hydrographs. As I showed you guys last time, we had an Excel sheet, and I showed to you, you can get this flow hydrograph from USGS, from a sensor data. So there are many sources that you can get these hydrographs from, but the one at USGS is called historical hydrographs. Like an event happened and you grab the data of this event. It is not based on return period. It's not based on data analysis. And I want to mention that some people, when they do flood hazard modeling, they do return periods for the queues. Like you have, for example, let's assume this is time, and this is Q. And over a course of 30 years, you will have like Q something like this. Like over 30 years, you keep getting events that has large Q in the stream. So you have a stream and there is a water that's flowing in this stream. This is how is the Q is a changing of the water. So you have this peak and this peak and this peak over a course of 30 or 100 years. People take these Qs and they make a return period of the Q, but this is not right because Q comes from the rainfall. So you will have to start with the rainfall, how much rainfall you get. And then you project the rainfall on and see how much Q that you get. So you cannot use this. So what we should use is time versus rainfall intensity, which usually is in inches or some meters or whatever. And you will have also something like this. Over a course of 100 or 30 years. So you start with the rainfall and you do data analysis to project what are you going to have in 100 years, after 100 years, how much rainfall you will get. So the 100-year event will be, for example, 10 inch of rain. So you take this 10-inch of rain, do hydrologic analysis, get the Q associated with the 100-year event, and then do hydrodynamic analysis, and you get the flood hazard map associated with a 100-year event frame. So this is how we get these events. Okay, so
there is a relationship between both water and
this relationship is very, very complicated. Like to do this, it's a hydrologic modeling. Many things can change. The land use can change. The soil can change. You can have urbanization in your area. So you will have to, in 100 years, there are many things can be changed. Okay, so you'll have to take this Q, run a hydrologic modeling. Take this rainfall, run a hydrologic modeling, and then get the new Q. But yeah, some people like rely on this Qs, but maybe it's not as realistic as you rely on the rainfall, because rainfall is the source of Qs. Okay, so flow data. Yep, okay. So here's the flow data that I have from last time, and this is for a 100-year event. Boundary condition 69C is in cubic meter per second, but my analysis is in cubic feet per second. Here is US customary. So let me save the geometry first file. So you will have to save the geometry data after you are done, and then I will close the geometry. Okay, next step is to add the unsteady flow data, which is the hydrographs, and I have my 3 boundary conditions. 2 of them are upstream, and they will have hydrograph, and one of them is the downstream will have normal depth friction. Okay, so the first one, let's start with Lumber River. You will have to click on your boundary condition, and you will assume it will be flow hydrograph. So you will click on a flow hydrograph, and then you will need to add the data of this flow hydrograph. So I have this data, as I told you, in cubic feet per second. It's very easy. You can take it, Control C. Let's close this. Control C, add, Control V. Let's remove this, delete. And I want to convert them from cubic meter per second to cubic feet per second. So basically, I will go to Google, and then I will say from meter cube to cubic feet per second. So you will find maybe any converter. Maybe I need to know what is the 1 meter cube equal to. Yeah, so this is the value. I will say that this cell is equal to this cell multiplied by the conversion. And if I want to plot it, like I can plot it here. I can plot this to insert. Yeah, so this is how the flow hydrograph look like in cubic meter per second. If I want the same hydrograph, this is cubic feet per second. So we have up to 45 cubic feet per second. This is how the hydrograph look like. So what I will do is I will go back to my unsteady flow data here, and I need to enter the start date of the flow. And since this is a return period, is not associated with a real event, so you can pick any start date. So the start date that we plug it in here last time is January 1st, 2000. And our data is every 1 minute. Then what I will do, I will copy this data, Control C, and I will paste them here. I will click on this one and I will put Control V. Then here it will you will have to put 0.05. This is called the slope for distributing flow along the boundary condition line. So you have your boundary condition line. So you have something like a factor. We usually take it 0.05. It's called how you distribute this flow along the boundary condition line. It's usually 0.05. And then we hit OK. Then we define our reverse boundary condition. And then we will do the same thing with Reed Springs. And then you identify the flow hydrograph. Also put the 1 minute and put the information for the flow, and then make sure that everything's right, put 0.05 and then hit OK. So right now we define our two boundary conditions. The third boundary condition, which is the downstream, that's the easiest one. So you click on this one and you define that this will be a normal depth. This is a downstream, not hydrograph. This is where the water is going out. So how is the water is gonna go out from this? You say that the water is gonna flow with a friction slope. This friction slope, we usually put it 0.01. And then we will hit OK. Right now, we defined all our boundary conditions, upstream and downstream. We will go.
Why don't have a hydrograph?
It's not a source of water. It's an outlet that the water goes out from. So once the water go from the upstream, we have a hydrograph. At the downstream, the water is going out. There is no water is going in. So this is an outlet that the water is getting out from. And all the water is getting out from this downstream boundary condition. So you are losing them from your model because your mesh only captured the water within the mesh. Even if it's not boundary condition, like let's assume that your mesh doesn't cover areas that should be covered. The water will go out from this area and you will lose this water. So that's why you need to make your mesh capture all the water, and all the water is going out from the downstream.
Do we have to like the depth of the water?
This is a good question. We sometimes do that. We call this base flow. Base flow. We sometimes do that. Then file, and then I will need to save this unsteady flow data. So file, and then you will save unsteady flow data, and you give this unsteady. I already saved it before. So if you want to save it as, you can save unsteady flow data as. But if you are saving it for the first time, save unsteady flow data, it will open a dialog box and you give it a name, like unsteady flow data Lumberton, and then hit OK, and it will be saved. Now I'm done with defining my boundary conditions. Like if I go edit unsteady flow data.
Now the sort, the flow see the river is empty, right?
Well, it depends on your digital elevation model. Usually the digital elevation model capture how is the state of the water. So this is on the top of the water. And then if I click on this, I just want to show you, if you want to see how the hydrographs look like. This is the one in Lumber River. And this is the one that is in Reed Spring Creek. So this is how the two hydrographs look like this way. If you want to show them in a table, you can click on this table and you will, not this table. Let's close this. If you click on this graphs, you will find plot and table. You can click on this table and you will see all the values of your hydrographs. This is a very important step. The next step is to run your analysis. Run, and you will find run unsteady flow analysis. You click on unsteady flow analysis. And then here, you will run, the programs will run the geometry processor and also unsteady flow simulation. I don't want to do sediment analysis. I want to do post-processor and also floodplain mapping. I want to run all of these. And then it will ask you, what is the start date and the end date of the run? So the start date is the start date of your hydrograph. However, the end date, it can be beyond the hydrograph. So even you can make the start date before the hydrograph or in the middle, you can make whatever you want, but it's better that you start with the hydrograph because this is when the water is gonna flow. But the end can be adjusted because if you have your flow hydrograph in the upstream, so this is when the water is in, but you want to see how's the downstream when the water is coming downstream. So you can extend the analysis after the hydrograph. Okay, so you put the start date and the end date and make sure that they have this format, like 0.01 January, and then you have 2000. If it's September, so SEB. Or you can click on the calendar and you just pick on the calendar because it has a specific format. And then it will ask you, what is the computation settings? I usually use 15 minutes, but you can go less than 15 minutes. So they ask you about the computation interval, the mapping output interval, the hydrograph output interval, and the detailed output intervals. So each one of these intervals, like the computing is how they compute the analysis. What is the time step? The mapping is when you have the simulation and you are running the simulation. You want to see the simulation each 1 hour or each 2 hours or each 15 minutes. And the same thing with others. It's reading the hydrograph. It's 1 minute. Do you want me to read it each 15 minutes? So I usually make them 15 minutes. Even in my hydrograph is 1 minute. But if I make it 1 minute when he runs the simulation, it will take much more time. And try if you want to like try and see if your code is working, or sorry, if your model is working, you might try with 1 hour and see if there's any problem. And then if it runs with 1 hour, you can go down. Yeah.
I was thinking, okay, if you can the value every 15 minutes, is there a chance that we miss that? I mean,
well, I don't think in 15 minutes you can miss it because 15 minutes is a very small interval. Yeah. But you can try, you can see, you can try 1 minute and 15 minutes, see how this will it change your analysis. Then once you are done, you will hit compute. And here's the time of truth. If once you start computing, it will take maybe a couple days, depends on like when I run a HEC-RAS simulation, I leave it in my office, keep running for like a couple days or 3 days, depends on your mesh time. However, some people like use a very large mesh and they only wait for like 4 hours. But for the running, so it will keep running the first phase and then the second phase. The first one is like checking the 2D mesh. Is there any problem with the mesh? Does the mesh doesn't capture your break lines? The boundary condition is not defined properly. So capture this, and then it will make an error that tells you there's some errors before starting the analysis. So some of the errors that you will get is that because your boundary conditions has problems, or some of the data that you have has problems, or your geometry has problems because sometimes we adjust the geometry while we are working, like I move points and stretch some points, then the program start remesh. So all this sometimes cause some problems. Other problems is related to the analysis. Sometimes when we do finite volume analysis, our analysis doesn't converge and it keeps running and making looping and keep running, trying to converge to an answer, but doesn't converge, and then close the loop, and then it sends you an error. So there are many errors associated. Some of them are aware of, some of them I'm not aware of. So I usually use communities like HEC-RAS communities on Facebook or actually on YouTube or any website, and then ask them questions because there's some errors that we can know, some errors that we can know. So if you get an error, you copy the error and then put it in Google, definitely you will find an answer. Some people had this problem before, okay? All right, so this is actually in brief how the HEC-RAS simulation will look like. So let's assume that our software run and we are getting a results. So let's see how's the result, how we can show the results. So once your model is run, you will find here that your models has, you will find like a summary of the analysis, and then you will close this tab. Okay, let's close it. And then once you close it, let's close this one as well. When you close it, you will go, let's assume, yeah, let's work with this one right now and close this one. Let's save project. Okay, let's assume that our model is running and we got results. Let's see how can we show results. Like after 2 days, we got results, and let's show the results. You will go back to the RAS mapper, the one that we added the train to it, and click on the RAS mapper. RAS mapper is the way that you get the output from HEC-RAS. You will get hazard maps for the flood depths, hazard maps for the flood velocity, hazard maps for the flood duration, everything about the results. Even let me tell you, you can create the mesh, the geometry on RAS mapper. You can do that if you want, but I feel some people use use RASMapper to do it, but I prefer to use the geometry. If you want to do it, you will find here on RASMapper the way that, in RASMapper, do you guys remember when we did the train? We click on trains and we create new RAS train and we bring the DEM model and we created the train model for our analysis. That's what we did at first. Like, let me show you. It was something like this train. Yeah, our train was something like this. Right? That's what we did first. Sometimes if you want to visualize this train in a discrete, like you want to see the difference between the levels, some people, they don't want the colors to be like melted on each other. So they do it this way, not stretch it, they make it discrete. And it will be something like this. So every elevation is separate, like everyone has like a range of colors. Okay, and for the geometry, if you came here at geometry, you will find that you can show your 2D area, like something like this. This is the geometry, the mesh. You can show it here. And you can add lines, like here you can click on the geometry and add new geometry or manage the current geometries. So you can do everything on RASmappers, but I usually use RASmapper for results, just to show results. Okay, let's assume that our HIC-RAS model has the results, and let's see how the results look like. Okay, let's see that this is our hazard maps, and you will find that the flood depths scenario is something like this. It's loading. Yeah, something like that. This one. This is the hazard map. The thing that you can actually show this on a base map, like you can add a base map, you can go to a map layer and add web imagery base map, and then you can show the ArcGIS world imagery base map. And if you click on it, you will see the base map below the hazard. So it will be something like this. So you can feel realistically where's the flooding is moving. And on the top bar here, if you want to, this is the maximum flood depths, but if you want to see how is the flood is evoluting, like is it changing over time, you need to click on depth like this and move this bar. This bar shows you how is the flood, is it changing? Like this. Can you see at the first like a few hours there is no flooding because I have zeros in my flow. If you look here, I have zeros, so there is no flow at these days until at few hours, and then at some time the flow start to move from the boundary conditions. And this is how is the flows moving from each boundary condition. Can you see I have 1 here, 1, 2, 3, 4, 5. Like this. And I don't have any problem. Like the water is flowing in the rivers without any flooding because I'm still like, didn't get to the peak. And at some point the water is peaking and there is overflowing from some places here. And let's see how is the water is flowing. Like, let's see how is the water, is it moving up or is it moving down? If you want to see the direction of the flow, you can click on this icon. And this icon will show you like how is the water particle is moving. If you want to adjust this like the size, the speed and everything, you can go to the this icon, sorry, this setting, like velocity setting, and then you can adjust the speed, you can adjust the density of these particles. If you want to make this speed is like this particles is much faster, Let's zoom in. Yep, and yeah, so you can adjust them from here. Like if you want to make them slow, you can come here, the density, like if you want to decrease the number of the particles, and then you will close this box. So you will see how is the water is flowing. Flowing very slow, right? Yeah, but anyway, I want you to look here. The water is moving this way and going up, right? However, I have boundary condition is getting water from here. So let's see how is the water is moving when a little bit earlier. Maybe more. Okay, so at first, the water is going down from this boundary condition, but it's still the maximum flow didn't hit from this line. So when the maximum flow get merged here with this one, the water will go up and change direction. That's very important that the hydrodynamic modeling is captured this phenomenon. So if a little bit here, after some time, I have my water start to moving up, and this area start to get some flooding. Also look here, this area is not getting flooding yet because there's a highway is blocking the water. But at some point, let's see, can you see how's the water step by step is then overflowing from the highway and then flood the other side of the city here. If your mesh is not extended at this location, because I have a hazard map that I ended the mesh with the highway, like my mesh is here, you will not be able to capture the flooding here because all the water is going outside of the mesh and you will not see that. That's why you try to cover as much stream as you can. Okay, so let's assume that our hazard map is good and we are ready to process this hazard map for our flood risk analysis. So what is the next step? Is to export this hazard map as a raster map and then use it for flood risk analysis. So I have many simulations like here. I mean, like I have a simulation each 15 minutes. Which one should I use? Like I use this or that. Which one should I use? I mean, like in terms of a raster map, I can import a raster map each 15 minutes, but I'm only interested in the maximum flood depths that happen in each 15 minutes. So there is a way to get this maximum. So if you want to see the maximum, you just click here on the maximum. This is the maximum flood depths. And this is the minimum flood depths, like there is no flooding. So I want to use this hazard map for my flood risk analysis because I'm only interested in the maximum flood depths that happen at each time step. So how to export this hazard map out of HICRAS? So first you will come here and click on this. And then you will, okay, you'll click on this one. Yeah, okay, yeah, here. So you'll click on edit map parameters. Let's click on this one. You will click here on edit map parameters and it will ask you what hazard map that you are interested in. So you can be interested in any hazard map at any time step, like at 15 minutes, at like January 6, January 7. But what I'm interested in is the maximum flood depths that happen for my entire analysis. So I hit maximum. And I want a raster-based train, like I want a stored hazard map and it's raster-based. I want a raster map of this hazard map, and then I will say save map. because this is what I'm interested in. And then I will click on this and I will say compute or update the stored map. So what I'm gonna do is I save that this is what I'm interested in. Right now, convert what I'm interested in into raster. Okay, so you click on compute and update stored map. It will take like a 1 minute to generate the raster based on the maximum flood depths that you have. Where can I find the stored raster map? You will go to the folder that you are saving your model in. So this model is saved here. Yeah. Not this. This. Lumberton. This one. And then it's yeah, here. So this is the 200 year or the 100 year. So you will go to every one that you run. You will find it in the same folder that you run, like something like this, 200 year, whatever the name of the hazard map. If you name your hazard map depths, you will find the folder. You open this folder, and then you will find a raster map like this. And the size will be like, let's see, what is the size of this map? Like 190 megabytes. Okay, right now we have a hazard map, right? So what is the next step? We need to do flood risk analysis. What was that?
No, saying we will go to ArcGIS to do the.
To do what? No, ArcGIS doesn't do fragility. ArcGIS will tell you the exposure. You overlay your buildings with the hazard map to identify the flood depths for each building. This is the first step. So what I'm gonna do is I will go to ArcGIS and then this is Lumberton. This is the community that I'm working on. Yeah, actually, this is the Bauer Transportation Network. Okay, here's it. Give me a message. We only it is like stored map depths maximum is created, and then I will hit OK. It's done. And now I need to prepare my buildings data. So let me clean this map first. All right, so this is my city, Lumberton, which has this blue boundary. And I have, these are my buildings. You can see them because they are very small, but let's zoom in. These polygons. Can you guys see them? All right. Okay, so these are the polygons. Let's click on this shapefile, open attribute table. And I have all this data about these buildings. I have number of stories, I have building archetype, I have building value, I have various floor elevation, I have all this information. So I need to overlay my buildings with the hazard maps. So I will drop my map on ArcGIS. So this is the map, and I will drop it here. And they will ask me about the projection. It will be WGS 1984. I will say, okay, close. And then this is the hazard map when we overlay it with the building. If you want to see all the hazard map or all your building, you click on the layer that you want to see. Claudia, so this is what you want to know to see the buildings. You click on the layer and then you say zoom to the layer. So you will see where's your layer at.
I did that. I
Okay.
discovered why I didn't see the fix.
Okay, so I saw everything. So this is my hazard map, but it's a black and white. And it has a range that tells you that the darkest black is the 0 elevation of water. The lightest is the highest elevation. If you want to change this colors, you can change them to blue to reflect water. So blue, but I want to make, yeah. So here's the darkest blue is the highest flood depths, like 6 meter flood depths. And the lightest blue is 0. And that makes sense because I have, here's my river is in dark blue and other areas that has been flooded is in light blue. So I make zoom in on my city. And if we want to test to see the flood depths at some locations, you can click on the identity button here, I, and then click at any pixel on your hazard map. So if I want to know what is the flood depths at this neighborhood, I click on this and it tells you it's 0.4 meter flood depths, like 1 feet meter. If you want to know at this neighborhood, it's 0.67 meter, which is 2 feet flood depths. 2 feet flood depths is huge. Like it can like ruin your appliances, furniture, if your building's on a slab grade foundation. And actually that's, to be honest, I have been to this community like multiple times and we did surveys for many of the people who live in these locations. They got really bad flooding from Hurricane Matthew and Florence. And actually Matthew and Florence is around 200, 500 year event. So this hazard map reflects what happened actually. Because this area is when we went and measured the high water marks at the building was around 2 foot at this neighborhood. So it's kind of representative of what happened in this neighborhoods. So right now I have my buildings in polygons and I have the raster map. How can I know the flood depths at each building? What should I do? 2 points, yeah, the first thing, and then extract the values at points. So to do this, I will go to Arc Toolbox. I will click on Arc Toolbox. It takes like a minute to load the boxes. And then I will go to feature 2 points. Feature. Two points. Yep, this one. And I have my building polygons here. I put my building polygons as an input feature and it tells you where do you want to save your output features. So you save them and name them wherever you want. So let's click here and go to our class, shape files, and let's say Lumberton. Let's name them Lumberton building points. Building points. Save, and then we will say okay. We'll take a minute. And then we'll close. All right, so this is, can you guys see the points? If you don't see the points and you want to see them clearly, you can click on the point and change the point format. You can increase the size of the point as much as you want. Like you can increase it to be 16 size, and then it will be something big like this. These are where the building points are, but this is very big. If you want to make it much more smaller, you can adjust the size. You can actually change the circle. It can be rectangle, can be triangle, whatever you are familiar with, you would like. All right, so the next step is to extract the hazard intensity at each one of these points. So I will go to calculate. Sorry, I will go to a spatial analysis tool, extraction, extract multi-values to points. And I will put the points in this input features, and I will put my rasters, which has the flood depths here. And I want to name the field as the depth 200, because this is a 200-year event. If you want to put the, because these values are in meter, so if we want to distinguish is it meter or feet, so I put meter like M, and then I will hit OK. Then here it will tell you exactly what is the flood depths at each one of these points. So if I go to the shapefile, open attribute table, I will go to the last field, you'll have the depths 200. Okay, so here we have the calculated flood depths, but you can see -999. What does it mean? Some buildings have flood depths -9999. That means that these areas didn't got flooded, so it has no data. Usually the no data is since this should be numerical, it doesn't tell you it's no data. It's about -999. Okay, so if you want to know the buildings that doesn't get flooded, you can rank these buildings from the lowest to the highest. So I double click on the top of the field, double click on this one, it will rank them from the lowest to the highest. If you double click one more time, it will make it from the highest to the lowest. Okay, so this is a one thing. So you will know where is the buildings that got maximum flooding. If you want to know the buildings that has negative flood depths or -999, you can go here, click on this one. It's called select by attributes, or you click here on the various icon, the table options, and you click select by attributes. So select by attributes, you will check the depths, this attribute, and I want to check what are the buildings that has flood depths less than 0. So this one, I click on this one, I click here, and I want to know if this value is less than 0. Apply. Here it will select all the buildings that has flood depths less than 0. So it check, basically the software is checking this condition row by row. And then it tells you here, right now I selected 17,000 buildings out of 20,000 buildings. So that means that 17,000 buildings are not exposed to flooding. And there's around the 3,000 buildings are exposed to flooding. If we want to see them, let's close this one and let's zoom in on this layer. Zoom to the layer. Let me change this color. Make it a little bit smaller. Right now, I only selected the buildings that are not exposed to flooding. So this is show, yeah. If you see here, all the points that are selected is outside the floodplain, and the one inside here, they are inside the floodplain, but they are not flooded because there's like maybe on a higher elevation or something. So let's make a close-up view on the buildings here and see how they look like. Let's make this very small, like let's zoom on these buildings and see what the state of flood depths at these buildings. All right, can you guys see? Not sure if you guys can. You'll find that the green ones is flooded, but this one is selected because it's in the floodplain, but there is no water around. There is no water here, there is no water there. Same thing here, and same thing at these buildings. So these buildings is not flooded. It's outside the floodplain, so they are not selected. Okay, so to be able to do processing, we need to convert these negative values to 0. because the flood depths at these buildings are 0. To do that, I will click on the shapefile, right click, open attribute table. And I want to have these buildings alone. Separate the flooded building from the non-flooded building. If you want to separate them, you can switch to this one. If you click in this one, you will only have the attributes of the non-flooded building or the selected buildings. So this one will take you to the selected building. Another trick, if you want to switch between the selected and unselected, if you click on this one, you will switch. The non-selected building will be selected and the selected will be not selected. Okay. Like if I click here on this one. So what happened right now? How many buildings are sorry? 2,353, which is the rest of the 20,000. And I unselect the 17,000 building, the non-flooded buildings. For me, I would deal with this building. What I do is, rather than running my analysis for 20,000 buildings, I know that 17,000 of these buildings doesn't have flooding, so it doesn't make sense to take them to MATLAB and let MATLAB do a 17,000 loops for buildings that doesn't get flooded. So what I do, I take these buildings that are exposed to flooding and export them alone and only do my analysis for these buildings alone. Unless if I'm working with a bunch of people that are studying the impacts of the flooded buildings on the non-flooded buildings, how this can happen. Like how the non-flooded buildings can impact, how the flooded buildings can impact non-flooded buildings. For example, if you have a school in the floodplain and it's a flooded, but it impacts other people outside the floodplain that send their kids to their schools. At this time, okay, I need to have my analysis for my entire region. I need to provide all the data and tell the guys, the social guys and economic guys, that this building is flooded and this building is not flooded. So I have to provide all the data. I couldn't exclude other or like the non-flooded buildings. But for our analysis, let's send or export the flooded buildings and deal with these buildings only. So to do this, you click on this shapefile that has the points and you will have data, export data. When you click on export data, it will ask you what data exactly that you want to export. Do you want to export only the selected feature? And if you click on this one, it will show you if you want to export all the data. So if I click on this, it asks you what kind of data you want to export. All the features, selected features, all the features in the view extent. So what I want to do, I want to export the selected only, right? Okay, so let's click selected. And then let me go here. And then building points, and then I will add flooded so that I can distinguish the flooded buildings from the non-flooded building. And then I will say save, and then I will hit OK. Oh, exporting error. I don't know why. But anyway, okay, let's look at this another time. We can deal with these buildings for now. Because I keep getting this error recently when I export only selected features. I don't know why, but let's work with all these buildings. So let's assume that we are working with the entire buildings, but after, like before I do that, let's make the negative values zeros. So what I'm gonna do is I'm gonna switch selection here. And I will convert all these negative values to 0. So I will make these values field calculator and I will put the depths as 0. So right now I don't have any negative flood depths value. And this makes sense because flood will never be negative. It's either flooded or not. Okay, so right now I have my 17,734 buildings have flood depths of 0. And I have the other 2,000 buildings have their normal flood depths. So what is the next step after knowing the flood depths of the building? To do risk analysis. Right now, we developed the hazard and height graph. And what we did right now, we did an exposure analysis. We identified which buildings are exposed, which buildings are not exposed, and what is the level of exposure? What is the flood depth at each building? What is the next step? Is the vulnerability. We need to do vulnerability analysis for these buildings. We need to know, with this flood depth that each building have, how much each building is vulnerable to have damage. And I told you before, maybe a building have a 2 or 5 feet flood depth, but it's 5 feet elevation from the ground. So it's not, this building is not vulnerable. But other building has 2 feet flood depth, but this building only elevated 1 feet from the ground. So it end up with having 1 foot. For this, we usually use not the depth grid. We call this flood depth grid. In flood risk analysis, we use what's called water surface elevation. This will save you lots of time. I think I told you guys this before. Like if this is my land, I mean like my ground. And what we have here is the depth grid, the raster maps that tells you the flood depths measured from the ground, right? This is the flood depth. But we can have the ground elevation. How can we get the ground elevations? From the digital elevation maps. And also we have what is called water surface elevation. These two, if I have these two, the ground elevation and the water surface elevation, we can get the flood depths. And that's actually what HICRAS did. We give HICRAS the depth grid, we give HICRAS the ground elevation from the depth, and HICRAS developed the train. And then HICRAS run his model and accounted for the water surface elevation, subtract the ground elevation from the water surface elevation and generated for us the depth grid. That's what HICRAS did. But what we want in our model is our buildings, maybe something like this. Maybe I have my building, something like this, and this is the water. And I'm interested in not the ground elevation. So this is the ground elevation. I'm interested in the first floor elevation, right? So what is better for me is to use water surface elevation, water surface elevation layer, or flood depth layer. It's better for me to use the water surface elevation layer because it will be very convenient for me to subtract the water surface elevation from the first floor elevation and identify what is the flood depth. But if I have the depth grid, it will be a little bit indirect. What you want to do is you want to have the ground elevation and sum the depths on the ground elevation to get the water surface elevation, and then subtract the water surface elevation from the first floor elevation to get the flood depths from here. Did you guys get it? Like if I have a building here, this is the FFE for, sorry, and this is my building. This is FFE for this building. And this is the water surface elevation. So basically, this is the ground. Measuring from the ground to the water surface elevation will get you the flood depths measured from the ground. But what I'm interested in is the flood depths measured from here. It's much easier for me if I know the water surface elevation and subtract from the FFE. So right now I get a positive value. But if the FFE is more than the water surface elevation, I will get a negative value. That means that this building is not exposed. So basically, I only work with ground elevation if I don't have FFE data. So I have to make assumptions. Like I have, as I told you before, I use the foundation, and from the foundation, and I assume the building height from the ground, and then go until I get the flood depths. But this is just the cases that I have. HICRAS give you water surface elevations. Like if you want, you can go to HICRAS back, and you will have water surface elevation data. Let's remove this. And let's get this. This is the water surface elevation. And you will find that the water surface elevation information here, if you look like here, you will find that the water surface is almost the same value, like 38, 38. The difference is very, very small between the water surface elevation from a point to another. It depends on, like, if we are talking theoretically, the water should make a one surface. It should be the same level. This is what the water should do. But because our land, the topography is not consistent. You have bridges, some areas the water is getting blocked behind the bridges and make a high water. It needs some times to get to another area. So there is a little bit differences between, like, you will find this area as a water surface elevation different from this area. Why? Because you have a highway. It blocked the water to move from here to here. So there is a little bit of difference. We can export this map and use this map for our flood depth analysis. So what actually I do in my analysis, I export the water surface elevation and extract the water surface elevation at each point. And having the FFE, I subtract the water surface elevation from the FFE and know the flood depths at each building point. But it's good to tell you that the FEMA hazard tool use the ground elevation for quantifying the flood risk analysis. So if I'm using FEMA hazard tool, I will using the depth grid that I showed to you and get the flood depths measured from the ground elevation and then get the damage analysis. But there's some other tools that using the verse floor elevation, and makes sense because this is when the flood start to make damage. Okay. Let's go back here. Okay, so here's an example. Let's assume that we have the water surface elevation maximum back at each building, and we have the FFE at each building. I believe I have it here. Yeah, here's the verse floor elevation at each building. This one and this field and this field. I can make a field, and I will call this field flood depths or depth FFE, means like a flood depth measured from the FFE. And I will change the field type to double. And I will say, okay. And then this field equal to, go to field calculator, FFE minus water surface elevation. This one. The flood depths will be this minus this. Okay. All right. Let's make it water surface elevation minus FFE. Water surface elevation minus.
I know there's WSC maps. Also,
well, actually, this long story, I have run multiple models, and like if you see, I have here. This is T4, means trial number 4, and was the best trial. So I'm using, but actually the differences is like very, very small, like not that big. So what I'm doing right now, if the water surface here and my building is here, I'm subtracting this from this and it will tell me this one. If the value is negative, that means is that this is more than that. So this building is not flooded. So I can exclude the negative. Okay, let's do this. Okay. Right, so I have many negatives here. Oh, these buildings, like it was a sample of buildings, but anyway, it's the same thing. Like these buildings are negative, so I can rank them from the highest to the lowest, And these values are in feet, so I can make them equal to 0 and then start my vulnerability analysis. So the idea from today's lecture is just to like, I'm almost there, is to get you familiar with how we develop hazard maps. And I showed you on HICRAS, and I can send you many videos. There are many ways, many people are explaining how to use HICRAS. So you can pick whatever one that you would like, and I need you to develop only one hazard map. All what you need is the digital elevation map and the flow hydrograph. Once you have these two, you can develop a hazard map by yourself. And you saw the steps. You just get the digital elevation map, develop the terrain, develop the geometry, identify the boundary conditions, and put flow in this boundary condition and run the analysis. That's it. We convert the flow, the flood depth and terrain.
That's for the homework.
Yeah, it will be one of the homeworks, but not this
okay.
one. Yeah. But also this will be for the project. So it will be kind of, I'm still developing the project. So like moving forward, all the homeworks that we'll do will be towards your project, but it will be like on tasks. So I will be giving you the DEM, digital elevation map, the flow data, and you will develop a HICRAS model. And I told you, you will develop a terrain, geometry, put the flow boundary conditions, run the model, get a hazard map. Once you get a hazard map, you need to export this hazard map as a raster, take this raster to ArcGIS, having the building shape files, put the polygons on the top of the raster, convert them to points, extract the water surface elevation, the flood depths at each one of these points. Then knowing the vertical floor elevation of each building, you can identify which buildings are exposed and which buildings are not exposed. And then next time, we will use the flood depths that we extracted to do vulnerability analysis using fragility. And we will do the same thing, like something similar to what we did with rain, but we will be using a flood fragility parameters. And I might start, I will show you the process, and then I will show you how we develop flood fragilities for flooding, like how the fragility is coming from component by component. So this may be like the 2 lectures of the next week. How did we develop flood fragilities, and then how can we use them for flood vulnerability analysis? Is that difficult? All right, so, okay, so yeah, I will upload the data on the Google Drive. You guys get the homework forward?
Yeah.
Did you guys check the data? All the data is there, right?
Yeah.
We're able to download the data?
We have the deadline for this Monday, right?
Yeah, you have,
Yeah,
Yeah.
it's possible.
Just over
but this is very simple.
these Monday.
I uploaded homework.
The day before the.
Oh, okay. Yeah. well,
We can extend it. You don't have to work the day before the midterm. Like I can give you a 2 days before the homework, like, so. Yeah, so you don't have to like work just before the day before, you can work before, but anyway. If you will not be able to get done before that deadline, we can extend it, no worries. Just like but not take that much time, okay?
Yeah.
Yeah, so yeah, I will be sending the data and start as soon as possible. This stuff is very, very important. Like, this is the most important piece of the course. Like, if you get what's going on and you know how to do it, you get how to work with ArcGIS, how to develop hazard models, you will be in a good place. So just do your best and don't worry about the deadlines. Deadlines are flexible. Like, I can extend it. Like, it's not like I'm gonna shoot you if you. Yeah.
I have a question regarding this one.
Okay, just
You-
let me
yeah.
stop the recording.